3 million light-years away, in the constellation Triangulum, a galaxy spins so fast it should have torn itself apart billions of years ago. This is the Triangulum Galaxy, officially catalogued as Messier 33 or M33. It is the third largest member of our small cosmic neighborhood, the Local Group, and every night it performs a celestial ballet that defies the fundamental laws of physics. It is a stunning 60,000 light-year wide spiral, but its elegant structure hides an impossible secret. The heart of the mystery lies in its rotation. According to Sir Isaac Newton's laws of motion, stars farther from the galactic center should move slower than those closer in. It's the same principle that governs our own solar system. Mercury races around the Sun, while distant Neptune crawls along its orbit. The gravitational pull weakens with distance, but M33 breaks these rules. Astronomers have measured the speed of its stars and gas clouds, plotting what is called a rotation curve. What they discovered was not a graceful tapering off of speed, but a terrifying consistency. Stars at the galaxy's edge move just as fast as, or even faster than, those closer to the center. It's the physics of a nightmare merry-go-round, where the horses on the outer rim are galloping faster than those near the hub. This rotational velocity creates an immense centrifugal force. By all accounts, M33 should be scattering its 40 billion stars and vast gas clouds into the intergalactic void like water droplets, flung from a spinning wheel. Yet, it remains whole, perfectly formed, and utterly defiant. Become a Stellify scientist. Like, subscribe, and join our cosmic exploration. Prepare yourselves. We begin. The Ghost in the Machine. Unmasking dark matter. The only way to reconcile this impossible speed with the galaxy's stability is to admit that the visible matter, every star, every glowing nebula, every detectable cloud of gas, accounts for only a tiny fraction of the gravitational pull required to hold it together. The remaining 90% of the mass comes from something invisible, something that does not emit, absorb, or reflect light, a ghostly substance that interacts with the cosmos only through its gravitational effects. We call it dark matter. The presence of this non-luminous mass was first postulated by astronomer Fritz Zwicky in the 1930s, but it was the meticulous work of Vera Rubin and Kent Ford in the 1970s, studying the rotation curves of spiral galaxies like M33 that cemented the hypothesis. Their observations demonstrated, beyond a shadow of a doubt, that a vast invisible structure must be gripping these galaxies. Dark matter forms an invisible, spherical halo that surrounds the entire visible galaxy. The spiral arms of M33 are embedded in this colossal, dark scaffolding. Its gravitational strength outweighs all the stars 5 to 1, preventing the entire structure from flying apart. The implications are staggering. Everything we see, every planet, every star, every familiar element, is merely a tiny fraction of reality. We are inhabitants of a cosmic city where 85% of the gravitational architecture is built from unseen foundations. The Triangulum Galaxy is more than a beautiful sight. It is a permanent laboratory where the universe exposes its most profound secret. Stellar behemoths, the crucible of creation. The Triangulum. Mystery is not just about the invisible, it's also about what is born in its brilliant glow. Deep within the galaxy's sweeping spiral arms, cosmic nurseries are giving birth to monsters. The largest and most spectacular of these stellar maternity wards is NGC 604. It is not merely a star-forming region, it is a colossal foundry of creation, shining with the combined intensity of 600,000 suns. Spanning over 1,500 light-years, NGC 604 is 40 times larger than the familiar Orion Nebula in our own galaxy, making it one of the largest H2 ionized hydrogen regions in the entire local group. Within this churning cauldron of gas and dust, gravity is sculpting stars so massive, they dwarf our sun like mountains dwarf pebbles. The lives of cosmic candles. The process begins in vast, frigid, giant molecular clouds. These are reservoirs of pristine hydrogen and helium, kept at temperatures just above absolute zero. Invisible to the eye, these clouds contain enough material to build millions of solar systems. The moment a shock wave, perhaps from a nearby supernova, or a collision between gas streams, disrupts the cloud, gravity takes hold with crushing inevitability. The cloud contracts, fragments into pockets, and as the gas compresses, it heats up. This is how protostars are born, but in the dense, chaotic heart of NGC 604, some of these protostars gather staggering amounts of material. They become O-type stars, stellar behemoths with masses 50, 70, or even 100 times that of our sun. These blue supergiants burn with temperatures exceeding 40,000 degrees Celsius, radiating a brilliant, searing blue-white light that is 50,000 times brighter than the star that warms our Earth. Their light is so energetic that it instantly ionizes the surrounding hydrogen gas, stripping electrons from atoms and causing the cloud to glow in electric shades of pink and turquoise. This is the origin of the nebula's iconic color. These giants, however, are living on borrowed time. While our sun is a steady conservative burner with a projected lifetime of 10 billion years, these colossal stars are cosmic Roman candles. They consume their nuclear fuel, primarily through the incredibly fast CNO, carbon-nitrogen-oxygen cycle, at an astounding rate. A blue supergiant burns through its fuel reserves in a mere 3 to 5 million years. They live fast and die young, barely having time to develop stable planetary systems before they exhaust their core and race toward their catastrophic end. Any nascent world orbiting one of these stellar titans would be sterilized by relentless, intense UV radiation long before life could even conceive of taking hold. Their fleeting existence is a necessary violence. In their brilliant, brief lives, these stars are the engine of chemical enrichment, forging heavier elements up to iron in their cores. Their eventual, spectacular deaths will scatter these elements across the galaxy, providing the raw materials for future generations of stars, planets, and ultimately, life itself. Hunters in the darkness, the black hole, Armada. Yet, even the brilliant terror of the blue supergiants pales in comparison to the dark predators that drift silently between the Triangulum Galaxy's spiral arms. These are the rogue black holes, the stellar mass remnants of the most massive stars that have been violently ejected from their birthplaces. A black hole is born when a massive star exhausts its fuel and its core collapses. If the star is heavy enough, the collapse is so profound that gravity overwhelms all other forces, compressing the stellar remnant into a region of spacetime from which nothing, not even light, can escape. This boundary is the event horizon, but how do these monsters become rogues? When a supernova explodes, the release of energy is often slightly asymmetrical. If the newborn black hole or neutron star receives a powerful directional shove, a kick from the uneven explosion, it can be launched out of its parent stellar system at speeds reaching thousands of kilometers per second. Now, they roam the Triangulum Galaxy alone. Each is a gravitational phantom with the mass of 10 or more suns, yet compressed into a sphere smaller than a city. They are completely invisible, silent, and deadly, detectable only when they actively devour something in their path. The Triangulum Galaxy is likely home to millions of these stellar mass black holes, the unseen graveyard remnants of ancient stellar epochs. The spectacle of consumption. The danger of a rogue black hole is not the speed of its passage, but the depth of its gravitational well. If a star, a gas cloud, or, horrifyingly, a planetary system ventures too close, the results are catastrophic. The black hole's gravity creates immense tidal forces, a differential gravitational pull that stretches and squeezes an object. If a planet crosses the event horizon, it is gone forever. But if a star approaches just outside that deadly boundary, it can undergo a tidal disruption event, TDE. The star is instantly stretched into a long, thin stream of plasma, a process called spaghettification. This stellar matter doesn't just vanish. It swirls into a superheated accretion disk around the black hole. The friction in this disk heats the material to millions of degrees, causing it to emit a brilliant flare of X-rays and gamma rays that can temporarily outshine an entire galaxy. These are the only times the cosmic predator betrays its presence, transforming from an invisible hunter into a blinding beacon of destruction. For any hypothetical civilization on a world in the path of a rogue black hole, the encounter would be apocalyptic. The black hole wouldn't need to directly hit the planet. Its immense gravity would instantly and chaotically disrupt planetary orbits, potentially flinging worlds into interstellar space, sending them crashing into their parent stars, or triggering global-scale geological upheavals through sheer tidal stress. The chilling truth is that these gravitational monsters are virtually immortal. They will persist in the cosmos long after the last star has died, and the universe has grown cold and dark, the ultimate cosmic predators in the final lonely epochs of spacetime. The elegant end, death as cosmic artistry. The Triangulum Galaxy is a realm where violence and beauty are two sides of the same celestial coin. Scattered throughout its spiral arms, delicate pink, blue, and green veils mark the final, gentle breath of dying stars. These glowing clouds are known as planetary nebulae. The name is a historical misnomer, coined by 18th century astronomers who thought the fuzzy, distant shapes looked like planets through their primitive telescopes. In reality, each one is a spectacular stellar death shroud. This fate awaits any star with a mass up to about 8 times that of our Sun, including our own. For billions of years, a star maintains a perfect, fragile balance between the inward, crushing force of gravity and the outward pressure generated by nuclear fusion in its core. But when the hydrogen fuel in the core is exhausted, the outward pressure vanishes. Gravity wins. The core begins to collapse and heat up, triggering a second round of fusion in a shell surrounding the dead core. This new energy source causes the star's outer layers to expand dramatically and cool, transforming the once stable sun into a bloated, brilliant red giant. The hourglass of elements. As the star continues to burn through its shell fuel, hydrogen and then helium, it becomes unstable. Deep within its structure, thermal pulses send shockwaves through the stellar atmosphere. These pulses gently but repeatedly blow off the star's outer layers in a series of expanding shells, like cosmic smoke rings spiraling into space. This ejected material, composed primarily of hydrogen, helium, and newly forged carbon and oxygen, forms a hollow shell around the core. Initially, this material is dark and cold. Then comes the moment of illumination. The star's superheated core is exposed, now a tiny, incredibly dense cinder called a white dwarf. This ember burns at temperatures exceeding 100,000 degrees Celsius, flooding the expanding shell with intense ultraviolet radiation. This UV light, strips electrons from the atoms in the shell, a process called ionization. Hydrogen atoms, when recombining, glow a deep red. Oxygen atoms glow brilliant green and blue. The result is a masterpiece, a cosmic stained glass window, painted in impossible, vibrant colors. Each planetary nebula is unique, telling the story of its parent star. Some form perfect spheres, while others create intricate structures like hourglasses, butterfly wings, or symmetrical jets, sculpted by the star's magnetic fields or the presence of a companion star. The timescales are poignant. The star lived for billions of years, but the planetary nebula phase lasts only tens of thousands of years. A brief, spectacular blink of a cosmic eye. As the shell disperses into the interstellar medium, it enriches the galaxy with the heavy elements forged during the star's long life. The carbon in our DNA, the oxygen we breathe, the nitrogen in our atmosphere, all of it was created in the nuclear furnaces of sun-like stars and distributed across the cosmos through the quiet, gentle act of a planetary nebula's fading light. We are, literally, recycled stardust. The furnace of gold, a supernova's cataclysm. Not all stars die with the gentle, artistic beauty of a planetary nebula. In the heart of M33's most active stellar associations, blue supergiants race toward an end that can outshine an entire galaxy in a single, blinding moment of stellar rage. The core collapse supernova. A blue supergiant burns through its hydrogen fuel with the intensity of a jet engine, converting 4 million tons of matter into pure energy every single second. The nuclear furnace in its core reaches astonishing temperatures, up to 50 million Kelvin. This extreme temperature allows the star to fuse elements far heavier than what our sun can manage. It operates in layers, like a cosmic onion. Hydrogen fuses into helium. Helium fuses into carbon and oxygen. Progressively heavier elements, neon, magnesium, silicon, are synthesized in shells surrounding the core. This process continues until the star begins producing iron. Iron is the atomic turning point. Its nucleus is so tightly bound that fusing it actually consumes energy instead of releasing it. The star's energy source, which has supported its colossal weight for millions of years, suddenly becomes an energy sink. The collapse and rebound. The star's fate is sealed. With the furnace extinguished, the outward pressure that battled gravity vanishes. What follows occurs in the space of a heartbeat. Gravity wins, catastrophically. The iron core, the size of Earth, collapses inward at 1/4 of the speed of light. In less than a second, it shrinks to a hyperdense sphere, barely the size of a city. The density becomes so extreme that protons and electrons are crushed together to form pure neutrons. The collapsing matter slams into this rigid, newly formed neutron core and rebounds, creating an unimaginable shockwave that rips violently outward through the star's outer layers. This is the supernova explosion. The blast wave expands at speeds of 30,000 kilometers per second, heating the surrounding gas to temperatures exceeding 1 billion degrees. In mere seconds, the supernova releases more energy than our sun will produce in its entire 10 billion year lifetime. But the most profound outcome is the creation of the heaviest elements. Elements heavier than iron, including gold, platinum, uranium, and every element necessary for technological civilization, are forged only in the final, violent moments of a supernova, through a process called the R process, rapid neutron capture, where the shockwave bathes surrounding nuclei in a dense flood of neutrons. The explosion enriches the Triangulum Galaxy with this precious heavy element seed, triggering the formation of new stars and distant gas clouds. What remains is determined by the star's original mass, a A star between 8 and 25 solar masses leaves behind a neutron star, an object so dense that a single teaspoon of its material would outweigh Mount Everest. A star over 25 solar masses leaves behind the ultimate remnant, a stellar black hole. Ancient sentinels, the globular clusters. To understand M33's future, we must look to its past, preserved in ancient stellar time capsules that orbit the galaxy like silent sentinels. These are the globular clusters, immense spherical collections of hundreds of thousands to over 1 million stars, tightly bound by their mutual gravity. They are among the oldest objects in the universe, true living fossils that formed when the cosmos was less than 1 billion years old. The stars within a single cluster, all roughly the same age, born in a single, rapid burst of star formation from a primordial gas cloud. But unlike the bustling NGC 6-4, these ancient nurseries were composed almost entirely of the simplest elements, hydrogen and helium, forged in the Big Bang. Heavy elements, astronomers call everything heavier than helium metals, were virtually absent. This chemical purity makes them metal-poor stellar systems, referred to as population 2 stars, living laboratories of time. The lack of heavy elements dramatically influences their evolution. Because they formed so long ago, only the smaller, longer-lived stars remain. The massive giants quickly burned out and exploded, leaving behind a dense population of smaller, reddish-yellow stars that will continue to shine for trillions of years. Globular clusters serve as magnificent cosmic chronometers. By analyzing the color and brightness of the stars within them, a technique called main sequence turn-off fitting, astronomers can determine their age with stunning precision. The oldest clusters in Triangulum are estimated to be nearly 13 billion years old, witnessing the entire history of galaxy formation from the cosmic dawn to the present day. These clusters did not form where we see them. They formed in the chaotic, turbulent environment of the young universe, in the dense cores of colliding gas clouds. Their distribution around M33 is not confined to the flat disk, but traces elongated, elliptical paths high above and below the galactic plane. These eccentric orbits map out the exact invisible shape of the galaxy's immense dark matter halo. They are, in essence, tracer particles, revealing the true three-dimensional structure of the gravitational scaffold that holds the galaxy together. The sheer density of stars in a cluster's core is phenomenal. If you stood on a hypothetical planet within one, the night sky would be ablaze with tens of thousands of stars, each one significantly brighter than any star we see from Earth. This extreme environment creates constant, close gravitational encounters, leading to the formation of exotic objects. Millisecond pulsars, rapidly spinning neutron stars, spun up by stealing matter from a companion star. Blue stragglers, seemingly young, blue stars formed from the merger of two older, smaller stars. And perhaps the deepest secret, evidence suggests some may harbor an intermediate mass black hole, IMBH, a black hole with a mass between 100 and 10,000 solar masses, a missing link between stellar mass and supermassive black holes. Cosmic highways, the physics of spiral arms. The Triangulum Galaxy's majestic spiral arms are not just beautiful decorations. They are cosmic highways, a persistent illusion driven by physics, not material structure. From our vantage point, the galaxy's spiral pattern appears fixed, like a frozen whirlpool in space. But if the arms were permanent features composed of stars and gas, they would have wound up completely, after just a few rotations, destroying the elegant pattern entirely. The solution lies in the spiral density wave theory. a revolutionary concept in galactic dynamics. The spiral arms are not fixed things, but waves of compression, like a traffic jam on a highway. Individual stars and gas clouds orbit the galactic center independently, but they momentarily slow down and pile up as they pass through the density wave. The star formation trigger. As material encounters the density wave, it is compressed, just like cars bunching up at a congested spot. This compression is the crucial ingredient that triggers star formation. Gas enters the wave. Compression squeezes molecular clouds. Gravitational collapse is initiated. New stars ignite. The brightest, hottest, and bluest stars, the blue supergiants, are born in the wave. They shine brilliantly, illuminating the spiral structure, but they die quickly, fading before they can drift far from their birth sites. This explains why the spiral arms are traced so perfectly by dazzling blue light. They are transient markers of a passing pressure wave. The entire process creates a cosmic conveyor belt of creation. Gas flows into the arms, is compressed into stars, and then the stellar winds and supernovae from those stars blow the remaining gas and newly forged heavy elements back into the space between the arms. The cycle repeats every few hundred million years as the galaxy completes a rotation. M33, specifically, is classified as a flocculent spiral, meaning its arms are patchier and less perfectly defined than a grand design spiral like our Milky Way. This suggests its spiral pattern may be temporary, driven by local instabilities or external gravitational forces rather than a long-lived, stable density wave. The arms also serve as channels for gas flow, gently directing material from the outer reaches toward the galactic center, ensuring that the galaxy continues to receive the fuel necessary for new star formation over billions of years. The visible light we capture is merely a snapshot of this eternal, dynamic process, a brief moment in the ever-shifting architecture of the Triangulum Galaxy, the unavoidable collision, Triangulum's fate. For all its impossible speed and defiant structure, the Triangulum Galaxy does not exist in isolation. Its destiny is tied to its massive dominant neighbor, the Andromeda Galaxy, M31. M33 is being slowly but relentlessly torn apart by the gravitational influence of M31. This is the effect of tidal forces, the same differential gravitational pull that creates our ocean tides, operating on a galactic scale with devastating effect. The side of Triangulum closest to Andromeda experiences a stronger gravitational pull than the far side, stretching the galaxy like cosmic taffy. This gentle, incessant stretching has been operating for billions of years. The most visible evidence lies in M33's outer regions, where streams of stars and gas have been pulled away, creating long, faint tidal tails that extend far into intergalactic space. These streams are a galactic wound, visible proof of the gravitational damage being inflicted by its massive neighbor. The three-way catastrophe. This slow tug is merely a prelude to the most spectacular collision in the history of the local group. In approximately 4.5 billion years, the Andromeda Galaxy will collide with our own Milky Way galaxy. It is an unavoidable head-on collision, with Andromeda currently approaching us at over 110 kilometers per second. The Triangulum Galaxy finds itself caught in the middle of this three-way cosmic catastrophe. As the third largest galaxy, M33 lacks the mass to significantly alter the main collision, but its fate is inextricably linked to the outcome. Computer simulations of the merger predict several possible fates for M33. Complete destruction. It could be entirely disrupted by the gravitational turmoil, its stars and gas scattered and mixed into the merging debris of the two giants. Survival as a satellite. its dense core might survive the initial chaos and be captured as a minor satellite orbiting the final merged supergalaxy. Direct merger. It might merge directly with the Milky Way or Andromeda before the main event, or as part of the primary collision. The merger itself will not involve stars smashing into one another. The distance between stars is too vast. Instead, it will be a chaotic gravitational ballet. The elegant spiral structures of all three galaxies will be completely destroyed, their stars flung into new chaotic orbits. The immense reservoirs of gas will collide and compress, triggering a final, massive starburst phase that will make the new galaxy one of the brightest objects in the universe for a brief period. The result of this 7 billion year long process will be a single, immense elliptical galaxy, a giant sphere of old stars that astronomers have nicknamed Milkomeda. Triangulum's distinct identity will be erased, its stars becoming an indistinguishable part of the new cosmic architecture, forever blending the hydrogen and helium forged in its ancient clouds with the elements created in the hearts of the Milky Way's giants. The ultimate horizon, dark energy, and cosmic isolation. The Triangulum Galaxy exists at a moment of transition, a vibrant middle-age system facing a catastrophic near-future collision. But beyond this local destiny lies the ultimate fate of the cosmos, driven by a force even more mysterious than the dark matter that holds M33 together: dark energy. Dark energy is the repulsive force that is accelerating the expansion of the universe. It is not matter or radiation, but a fundamental property of space itself, making up roughly 68% of the total energy density of the cosmos. The discovery of this accelerated expansion in the late 1990s revolutionized cosmology, showing that the universe is not merely slowing down after the Big Bang, but is being pushed apart at an ever-increasing rate. The future of astronomy. The Triangulum Galaxy, the Milky Way, and Andromeda are gravitationally bound within the local group. Their mutual gravity is powerful enough to overcome the outward push of dark energy, which is why the collision is inevitable. But beyond the local group, everything else is being pushed away from us at tremendous speed. This has profound implications for the far future. Billions of years from now, astronomers in the merged Milkomeda galaxy will look up at a much emptier night sky. All the distant galaxies we observe today, the spectacular clusters, the millions of spiral and elliptical systems, will have receded beyond our cosmic horizon. The light from those distant objects will never reach us. They will effectively disappear, leaving Milkomeda in a cosmic island, isolated from the rest of the universe by the accelerating expansion of space itself. For any civilization that arises in that far future, the clues to the universe's origin, the evidence for the Big Bang, the measurement of the Hubble constant, will be much harder to find, erased by the relentless march of dark energy. The search for the nature of dark energy is the single greatest challenge in modern science. If its strength remains constant, the universe will expand and cool forever, ending in a frozen big freeze. But if its density increases over time, it could eventually overcome all other forces, tearing apart galaxies, stars, planets, and even atoms in a catastrophic event known as the Big Rip. The Triangulum Galaxy, therefore, is not just a beautiful system of stars and gas. It is a brief, glorious structure, poised between the certainty of a local, gravitational collision and the terrifying uncertainty of a cosmic fate, driven by the unknown energy of the vacuum. Cosmic archaeology, tracing the quantum whispers. The existence of the Triangulum Galaxy, in all its majestic complexity, owes its existence to the most microscopic fluctuations. in the fabric of space-time that occurred at the universe's earliest moments. We are talking about quantum fluctuations, the tiny random variations in energy density that were present when the universe was smaller than a single atom, governed by the strange laws of quantum mechanics. At this scale, the notion of empty space breaks down, replaced by a boiling foam of virtual particles, appearing and disappearing instantly. These microscopic ripples were the seeds of all cosmic structure. From atom to galaxy, the universe underwent a period of astonishing exponential growth called cosmic inflation, lasting just a fraction of a second. This rapid expansion had a revolutionary effect. It stretched those quantum scale fluctuations to astronomical sizes. Regions that were once separated by distances smaller than a proton were suddenly separated by light years. The tiny quantum uncertainties of the initial universe were inflated into the vast, large-scale density differences we observe today. These differences were tiny, variations of just 1 part in 100,000, but they were enough. The slightly denser regions had a stronger gravitational pull, forming the gravitational wells that allowed matter to collapse. The Triangulum Galaxy, along with every other galaxy, star, and planet, is the ultimate macroscopic expression of this initial quantum uncertainty. Its spiral arms, its stars, and its dark matter halo are all monuments to a physics experiment that occurred on the smallest possible scales. The resulting structure is the cosmic web, a massive, three-dimensional network of filaments and voids that spans the entire observable universe. Galaxies are not scattered randomly. They sit along these filaments, which act as cosmic highways of dark matter and gas, channeling material into dense nodes where massive clusters form. The Triangulum Galaxy and the local group sit within one of these smaller filaments. Our galactic neighborhood is a tiny nexus within a scaffolding that stretches for billions of light years. The entire journey of M33, from the formation of its first metal-poor globular clusters to its impending merger, has been dictated by its position within this vast underlying structure, a blueprint written in the quantum foam of the first second of time. The interstellar medium, the galactic ecosystem. The life and death of stars within M33 are dictated by the swirling, complex material between them. The interstellar medium, ISM. The ISM is not a uniform void. It is a dynamic, multi-phase ecosystem of gas, dust, and cosmic rays. It is the blood and breath of the galaxy, carrying the raw fuel for creation and the processed debris of destruction. The ISM exists in 4 main phases, each in thermal and pressure equilibrium. Cold molecular phase, the densest, coldest clouds, giant molecular clouds, where star formation occurs. Cold. Neutral phase, patches of neutral atomic hydrogen, HI, that are still too cold and clumpy for fusion. Warm, neutral notch ionized phase, a pervasive medium that fills most of the galactic volume. Hot ionized phase. Superheated, extremely low-density gas created by supernova shockwaves containing temperatures up to 1,000,000 Kelvin. The ISM acts as a giant chemical processing plant. Star formation consumes the cold molecular gas, and stellar death, supernovae and planetary nebulae, replenishes the ISM with hot, chemically enriched gas. This process is called galactic recycling. Galactic fountains and stellar winds. Massive stars in regions like NGC 694 generate powerful stellar winds, streams of high-velocity charged particles that can carve out enormous cavities in the surrounding ISM, creating vast superbubbles hundreds of light years across. When a supernova explodes, it drives this hot gas even higher, sometimes breaking through the flat galactic disk entirely and into the surrounding galactic halo. This is the galactic fountain effect. The enriched material rises, cools, and eventually rains back down onto the disk, seeding new regions with the heavy elements needed for the next generation of stars and rocky planets. The dust grains, though only 1% of the ISM's mass, are crucial. They act as cosmic shields, blocking ultraviolet radiation and allowing molecular clouds to cool sufficiently for gravity to take hold. They also act as catalytic surfaces, allowing simple atoms to combine and form complex molecules, including water, alcohols, and organic compounds, the chemical precursors to life. The entire Triangulum Galaxy is a single, self-regulating ecosystem. Its rotation, its dark matter halo, its spiral arms, and its violent star formation all combine to stir the ISM, ensuring that the elements necessary for complexity, for planets, for chemistry, for life, are distributed throughout the vast spiral. M33 is a cosmic machine designed for one purpose: to take the simple hydrogen of the Big Bang and transform it into the complexity of the chemical periodic table. The final mystery. Our journey through the Triangulum Galaxy, Messier 33, began with an impossible question. How can a galaxy spin so fast without tearing itself apart? The answer required us to confront the deepest challenges in cosmology: the dark matter that provides the invisible scaffold, binding the galaxy in defiance of conventional physics. The stellar behemoths of NGC 604, which live brief, violent lives, only to enrich the cosmos with the heavy elements forged in their cores. The rogue black holes, the gravitational shadows that drift silently, embodying the ultimate destructive power and longevity of the universe. The graceful elegance of planetary nebulae, demonstrating that even the death of a star can be an act of cosmic artistry, essential for the cycle of life. The physics of spiral density waves, which create the illusion of permanent sweeping arms, where creation is a continuous, transient process. The certain fate of a galactic merger, where M33 is caught between the Milky Way and Andromeda, its identity set to be erased in the birth of a new, colossal galaxy. The dominant, repulsive force of dark energy, which will eventually isolate our cosmic neighborhood, making the rich history of the universe a distant, unreachable memory. The Triangulum Galaxy has served as our guide through the extremes of space-time. It showed us the fundamental balance between gravity and expansion, creation and destruction, the visible and the invisible. It revealed that everything we see, every element in our bodies, every planet in our sky, is the result of billions of years of cosmic alchemy and recycling. The final mystery remains. Somehow, in this small, vibrant corner of the cosmos, matter has organized itself into forms capable of contemplating the cosmic whole. We are the galaxy's way of understanding itself, conscious observers, decoding the history written in starlight, X-rays, and gravitational waves. The greatest secret of the Triangulum Galaxy is that the universe is capable of knowing itself through minds like ours. The adventure of cosmic discovery never ends. Each question answered simply opens a new, deeper frontier to explore, a new mystery to unravel. Do not let the mysteries of the universe fade into the void. Stellify Science is your home for decoding the impossible, from the smallest quantum particles to the largest galactic empires. The Triangulum Galaxy is just one of countless wonders waiting to be explored. If you were captivated by the secrets of dark matter, the terrifying speed of blue supergiants, and the ultimate fate of our local universe, then you are a true Stellify scientist. Smash that like button and subscribe to Stellify Science right now. Hit the notification bell so you never miss our next deep dive into the cosmic unknown. And here's your final challenge. In the comments below, tell us, If you could pilot a probe into the heart of NGC 604, what single question about massive star formation would you ask? Subscribe, explore, unravel the universe with Stellify Science.